For our final bridge testing, we recorded from the front and the side. Our bridge reached a total weight of 20 kilograms before failure. This is a side angle shown frame by frame. The top cross member on the right is the first point of failure. After failure of the right top cross member, the right-sided base fails as it is no longer supported. Failure of the top cross member can also be seen from the front angle. There are many variations of truss types, some simple and some complicated. Due to spaghetti being a difficult building material, we wanted to choose a simple design. This led us to investigating the wattle truss, Warren truss, Pratt truss and Howe truss. The Warren truss was patented in 1848. Equilateral triangles are used to spread out the loads of the bridge. For a central weight, this bridge is stronger if the weight is placed on top in comparison to the base. Using the bridge designer software provided by Johns Hopkins University, we were able to calculate the compression and tension forces on each member. The Pratt truss was designed by Caleb and Thomas Pratt and patented in 1844. The design quickly grew in popularity and is still well known today. The Pratt truss had slightly less compression in comparison to the Warren truss. This made it a better design for our building material. The Howe truss was designed in 1840 by William Howe. It is better suited for bridging longer spans than a Pratt truss, and because of this it became popular for use within wooden railroad bridges. Many Howe truss bridges are still used today. The Howe truss is very similar to the Pratt truss. The only difference is in the angles of the inner members. The compression and tension forces are switched. Less compression occurs, but the compression members are longer, so there is no real advantage for using this design. Designed by John Alexander Waddell in 1898, this triangular truss is a minimal design with very few members. The wattle truss only contains 2 compression members, 3 tension members and 2 zero force members for bracing. This design was found to be best suited for our requirements. Our final design incorporated the wattle truss, but we decided to build around the weight plate as we didn't need to consider live loads. We used SkySieve.com to calculate the member loads of our final design. The member loads allowed us to calculate the required thickness of each member based on the loading. The thickness of each member was built as pictured below. As most of the members were circular in shape, joining opposing members was far more difficult compared to using a square-shaped design. This would later affect the end result of our bridge due to unsymmetrical sides. Once all members had been individually made, they were ready to be glued together. Some of the ends needed to be cut off at the correct angle to connect as the isosceles triangle. A stencil of our truss was used for reference when cutting and gluing. This helped to make sure all the triangles were of equal dimensions. Lateral bracing was used for keeping the 2 sides of the bridge together and also preventing twisting. Only bracing was required for the top and side members. This is because they were all compression members and will deform much more than the tension members on the base. Besides joining the 2 sides, the lateral bracing strengthens the bridge significantly, as it also shortens the compression members. This is because halving the length of a spaghetti compression member increases its strength by a factor of 4. The use of gusset plates on the joints of a truss helped to join members and support each joint. During construction, when joining the members, we were concerned the joints would be weak due to uneven joins from cutting. Using individual strands of spaghetti across the joins, we were able to simulate a gusset plate on our bridge. These strands are zero-force members, but when the bridge begins to deform under load, they help to prevent buckling of compression members and also carry some loads. The most noticeable change to improve on would be the symmetry of our design. After gluing each side of the truss together using the stencil, we noticed the two sides were out of alignment. At this point we did not have time to fix the issue, but we knew the bridge would not hold its maximum potential as the load distribution would be significantly uneven. This was caused partly by rushing, but also difficulty joining the circular members. It was extremely hard to keep them from rolling when cutting and gluing. The use of square members would have given more accurate connections. The top cross member was the first point of failure. Due to weight restrictions, we could not thicken this member as much as we would have liked to. Building a thinner base would have allowed for a thicker top cross member. Although the truss calculations showed the base was under minimal tension in comparison to other members, we still built a thick base. This was due to concerns of supporting the weight plate. Having more confidence in our calculations and strengthening the relevant members under the greatest loads first would achieve better results if tested again.